It's kind of wild when you think about it. Light, I mean, it's everywhere. We see because of it. But what is it really?
Yeah, you sent over this chapter on the nature and propagation of light. Really interesting stuff.
Totally. So for this deep dive, I figured we could unpack some of the key ideas about how light works, what it is, how it moves, and how it makes stuff like rainbows.
Great idea. And what's especially cool about light is that we've understood it in like completely different ways over time.
Right.
Like the chapter starts off talking about how people used to think of light as these little particles.
Oh, yeah. Almost like bullets flying out from a light source.
Exactly. Simple and kind of makes sense, right?
Yeah.
But then in the 1800s, things got more complicated.
Yeah, I remember that part, like how light bends around things, diffraction, I think it's called, and how light waves can like add up or cancel each other out.
Yeah,
Makes it tough to think of it just as particles.
totally. And that's kind of what led to the whole idea of light being a wave. Then, in the 1870s, comes James Clerk Maxwell, and he like blew everyone's minds.
Yeah, Maxwell was a genius. He basically figured out that electricity and magnetism were connected. Not separate forces, but two sides of the same coin. Electromagnetism. And get this, his equations predicted these waves, electromagnetic waves, that acted exactly like light. Pretty huge.
Well, yeah, absolutely groundbreaking. And later on, Heinrich Hertz actually went and made these electromagnetic waves in the lab, like proof. So, okay, light's a wave, but where do these waves actually come from?
Well, the chapter talks about how accelerating electric charges make them. Think about like the electrons in a light bulb's filament. They're constantly jiggling around and emitting these ripples of light.
Exactly. And the chapter breaks down a few main sources of light. You've got thermal radiation, which is basically anything hot glowing, right? Like a stovetop burner.
Oh, yeah, yeah. And that's just because heat makes the atoms and molecules vibrate, and those vibrations involve charged particles moving around.
Right. And those moving charges give off electromagnetic radiation, which can be light if it's hot enough. Then there's electrical discharges, which are like super bright flashes. Think lightning or those cool neon signs.
Those are so cool. And that's when electricity goes through a gas, kind of excites those gas atoms, and they give off specific colors of light depending on the gas.
You got it. And then we've got lasers, which are kind of in a league of their own.
Lasers are like science fiction come to life, but they're also super useful in the real world.
What makes lasers special is that their light is all in sync. It's what we call coherent, like an orchestra where everyone is playing the same note perfectly together.
Ooh, that's a good analogy. Makes sense why they're so focused and powerful. But here's the thing, right? Even though we've got all this evidence for light as a wave, it also acts like a particle. It's like it can't make up its mind.
Yeah, that's the whole wave-particle duality thing. It's a central idea in quantum mechanics, and it basically says light can be both a wave and a particle, depending on how you're looking at it. It's like trying to describe a coin as only heads or tails when it's really both at the same time.
Makes my brain hurt a little, but that's quantum mechanics for you. The chapter even mentions these tiny packets of energy called photons or quanta, like light comes in these little bundles.
Right, so when light is traveling through space, it acts like a wave. But when it interacts with matter, like when it hits something, it's those photons that do the interacting. And the energy of a photon is connected to the frequency of the light wave. So higher frequency means more energy per photon. That's why blue light is more energetic than red light.
Interesting. So blue light packs more punch in those little packets. And the chapter touches on this thing called quantum electrodynamics, or QED, which sounds pretty intense.
Oh yeah, that's the really deep theory about how light and matter interact on a quantum level. It brings those wave and particle ideas together. It's complex, but super successful.
Pretty incredible stuff. So, okay, we've talked about the dual nature of light, which is pretty mind-blowing on its own, but how does light actually travel, like physically move through space?
Well, the chapter introduces the concept of wave fronts. Think of it like ripples in a pond. When you drop a pebble in, you get these circular waves spreading out. Each of those ripples is like a wavefront. It connects all the points on a wave that are vibrating together.
Oh, okay. So if you had a point source of light, like a tiny light bulb, and it was in a perfectly uniform material like air or clear glass, the wavefronts would be these expanding spheres.
Exactly. The light travels outwards in all directions at the same speed, so at any moment, all the points the light has reached form a spherical wavefront.
Makes sense. But the chapter also talks about plane waves, which are like flat, right? How do those come about?
Imagine you're standing super far away from that light bulb. If you look at just a tiny part of that huge spherical wavefront, it'll look pretty much flat. Like the Earth seems flat to us because we're so close to the surface. So even a spherical wave can look like a plane wave if you're far enough away.
Makes sense. Now, the chapter also talks about rays, which are those straight lines we often see in diagrams.
Right. Rays are kind of a tool we use to simplify how we think about light. They show the direction the light energy is traveling. In a uniform material, those rays are always perpendicular to the wavefronts.
Oh, okay. So, like, for a spherical wavefront, the rays would be sticking out in every direction, like spokes on a wheel.
Exactly. And for a plane wave, the rays would all be parallel to each other. And the chapter talks about something called geometric optics, which uses rays to understand things like lenses and mirrors.
Makes things easier to picture, I guess. But then there's also physical optics, right? What's the difference?
Well, geometric optics works great when you're talking about stuff that's much bigger than the wavelength of light. But when you get down to really tiny things, like the size of light waves themselves, things get more complex.
Like you start seeing all that bending and interference stuff again.
Right. That's where physical optics comes in. It takes into account the wave nature of light to explain those phenomena.
Yeah.
So yeah, there are different ways to think about how light travels depending on what you're looking at.
Makes sense. So we've got light traveling as waves, sometimes acting like particles. But what happens when that light hits something, like a boundary between two different materials? I know the chapter goes into reflection and refraction.
Exactly. When light hits a smooth surface, like going from air to glass, some of it bounces back, that's reflection, and some of it goes through, but it bends, that's refraction.
Okay, and there are two types of reflection, right? Specular and diffuse.
You got it. Specular reflection is what you get from a really smooth surface, like a mirror. The light bounces off in a nice, predictable way. Diffuse reflection is what happens with rough surfaces. The light scatters all over the place. That's why you can see things that aren't shiny from any angle.
Right, the light is bouncing off in every direction, but the chapter focuses more on specular reflection, right?
Yeah, because it's a bit more straightforward to understand. And there are these laws of reflection that govern how light bounces off smooth surfaces.
Like what?
Well, first you imagine a line perpendicular to the surface, called the normal. The angle between the incoming light ray and the normal is the angle of incidence. And the angle between the outgoing reflected ray and the normal is the angle of reflection.
Okay, so it's all about angles.
Yeah, and the law of reflection says those two angles are always equal. And the incoming ray, the reflected ray, and the normal all lie in the same plane. It's pretty neat and orderly.
So like a perfect bounce. Okay, so that's reflection. What about refraction? That's where light bends when it goes from one material to another, right?
Exactly. And the reason it bends is because the speed of light changes in different materials. Light travels fastest in a vacuum. And when it enters a material like glass or water, it slows down.
So different materials slow light down by different amounts.
That's right. And that's where the index of refraction comes in. It's basically a measure of how much a material slows down light. It's always greater than 1 because light never travels faster than it does in a vacuum.
Okay, so a higher index of refraction means light slows down more in that material.
Exactly. And this change in speed at the boundary between two materials is what causes the light to bend, to refract.
Yeah.
There's this law called Snell's law that describes exactly how much it bends based on the indices of refraction of the two materials.
So Snell's law is like the rule book for how light bends.
You got it. It tells us how the angles of incidence and refraction are related. Like if light goes from air into glass, it bends towards the normal, that imaginary perpendicular line we talked about.
Oh.
Ah, okay. Because it's going into a material with a higher index of refraction, so it slows down. What if it goes the other way, from glass into air?
Then it bends away from the normal because it speeds up. You can kind of think of it like a marching band walking from a sidewalk onto a muddy field. The side that hits the mud first slows down, causing the whole band to swing towards the mud.
That's a great way to picture it. So the light bends, but the chapter also says its frequency stays the same, but its wavelength changes. How does that work?
Well, the frequency of a wave is how many times it vibrates per second. And that's determined by the source of the light, like the light bulb. So when light goes from one material to another, its frequency doesn't change, but its speed does, and that affects its wavelength, which is like the distance between the crests of the wave.
Oh, so it's like the same number of vibrations per second, but those vibrations are spaced differently because the speed is different.
Exactly. The wavelengths get shorter when light goes into a material with a higher index of refraction. Okay, now let's move on to something super cool. Total internal reflection. This is where light can get trapped inside a
Oh
material.
yeah, I remember this. It's like an optical magic trick. How does it work?
So it happens when light tries to go from a material with a higher index of refraction to one with a lower index, like from glass to air.
Yeah.
And it has to hit the boundary at a really steep angle, larger than something called the critical angle.
So two conditions, going from high index to low index and hitting the boundary at a steep angle.
Right. And if those conditions are met, all the light gets reflected back into the first material. None of it escapes.
Like it bounces off the inside surface completely.
Yeah.
So cool. But it's not just a cool trick, right? The chapter mentioned it's used in all sorts of technology.
Absolutely. Like in binoculars, they use prisms that rely on total internal reflection to bounce light around, and fiber optics, which are those super thin glass or plastic fibers that carry light signals over long distances.
Oh yeah, they're used in everything from the internet to medical imaging.
Right. And think about diamonds. They're so sparkly because of total internal reflection. Light gets trapped inside them and bounces around before finally coming out.
Wow, so it's not just cool physics, it's super practical too. Okay, what's next?
How about dispersion? This is what makes rainbows possible. Basically, the index of refraction isn't actually constant for all colors of light. It changes slightly depending on the wavelength.
So different colors of light bend by different amounts when they go through a material.
Exactly. And that's why white light, which is a mix of all colors, gets split into a rainbow when it passes through a prism. Each color bends at a slightly different angle.
And that's why diamonds are so sparkly too, right? They have a high index of refraction, so they trap light, but they also have a lot of dispersion, so they spread the colors out.
You got it. And rainbows are a perfect example of dispersion in action. When sunlight goes through raindrops, it gets refracted and dispersed, splitting into all the colors. And some of that light reflects back out of the raindrop, creating the rainbow we see.
It's pretty amazing how those little raindrops can act like tiny prisms. Okay, let's move on to something that's maybe a bit less obvious but still super important. Polarization.
Polarization is all about the direction that light waves are vibrating. It's kind of like how a guitar string can vibrate up and down or side to side. Unpolarized light is vibrating in all directions at once.
So it's kind of a jumbled mess of vibrations.
Exactly. But we can filter out some of those vibrations and create linearly polarized light where the light is only vibrating in one direction. And we do that with polarizing filters.
Like polarized sunglasses?
Yep. Those block certain directions of light, which can reduce glare. And there's this law called Malice's law that describes how much light gets through a polarizer, depending on the angle of the filter.
Okay, so the angle of the filter determines how much of the light gets through. And there's also polarization by reflection, right? Like how light reflecting off water can be polarized.
Exactly. And there's a specific angle called Brewster's angle, where the reflected light is completely polarized. This is used in some photography techniques, and is also why polarized sunglasses work so well for reducing glare from water. They block the horizontally polarized light that's reflected off the surface.
So polarized sunglasses are basically just fancy filters that block certain directions of light. Pretty cool. The chapter also mentions circular and elliptical polarization, which sound pretty complicated.
They are a bit more advanced, but basically they happen when you have two linearly polarized waves that are perpendicular to each other and out of sync. It causes the direction of the electric field to rotate, tracing out a circle or an ellipse.
Oh, okay, so it's like the light is spiraling as it travels. Interesting. All right, moving on. How about the big question?
Yeah.
Why is the sky blue? The chapter talks about scattering, right?
That's right. Scattering is when light bounces off tiny particles in the atmosphere, and different colors of light scatter differently. Blue light scatters more than other colors, which is why we see a blue sky.
So it's not that the sky is actually blue, it's that the blue light is bouncing around more.
Exactly. It's called Rayleigh scattering, and it's stronger for shorter wavelengths of light, like blue and violet. And that scattered light is also polarized, which is why polarized sunglasses can reduce glare from the sky too.
Makes sense. But what about sunsets? Why are they red and orange?
Well, when the sun is low on the horizon, the light has to travel through more of the atmosphere to reach us, and all that blue light gets scattered away, leaving mostly the reds and oranges, which have longer wavelengths and don't scatter as much.
So it's like the atmosphere is filtering out the blue light, leaving the warmer colors. And the chapter also talks about why clouds are white, which seems kind of counterintuitive since scattering makes the sky blue.
Yeah, but clouds are made of much larger water droplets or ice crystals. And those larger particles scatter all colors of light equally, so we see white.
Okay, so it's all about the size of the particles that are doing the scattering. Cool. Now, last but not least, the chapter introduces Huygens' principle, which is about how waves spread out.
Huygens principle basically says that every point on a wavefront acts like a new source of waves. So you can imagine the wavefront kind of building itself up from all these tiny wavelets spreading out from each point.
Oh, I see. It's like each point on the wave is sending out its own little ripples.
Exactly. And you can use this principle to predict how waves will travel and bend and interact with different things. It's a pretty powerful tool.
Pretty cool stuff. And the chapter even mentioned that you can use Huygens' principle to understand those laws of reflection and refraction we talked about earlier. It's like bringing everything full circle. Okay, well, that was a whirlwind tour of the nature and propagation of light. What are some of the key takeaways you think are most important to remember?
Well, first, the whole wave-particle duality of light is mind-blowing. It's like light plays by its own rules, and then understanding how light bends and reflects and interacts with different materials is crucial for understanding how everything from lenses to rainbows to fiber optics works.
Absolutely. It's amazing how these fundamental principles explain so much of the world around us. And the fact that our understanding of light is still evolving is pretty exciting. Who knows what other mysteries we might uncover in the future? Well, I think we've covered everything from the chapter on the nature and propagation of light. Thanks for joining me on this deep dive. It was illuminating, to say the least.
It was my pleasure. Light is a fascinating topic. There's always more to learn.